Hello everyone, welcome back to differential equations. Last time we had just finished up the method of undetermined coefficients. And that method applies to linear differential equations with constant coefficients, but where the right-hand side of the equation is a combination of polynomials, exponentials, and sines and cosines. And what makes those functions so special is that when we compute the derivative of polynomials, we get another polynomial. When we compute the derivative of sine and cosine, we get sines and cosines. When we compute the derivatives of exponentials, we get exponentials. As we noted at the outset of the previous lecture, they reproduce according to their kind. Well, you know what? A lot of functions in mathematics don't reproduce according to their kind. And in that situation, the method of undetermined coefficients just doesn't work. So instead, we use the technique called variation of parameters, because some do not reproduce according to their kind. Boy, nothing's ever simple, is it? Let's look at some background information, though. Some don't reproduce according to their kind. For example, secant of x. Derivative of secant of x is secant x tangent x, and the derivative of secant x tangent x, oops, this is a product rule thing coming in, so let's see, we're going to get first times derivative of the second. What's derivative of tangent is? We need another quiz. Oh well. Derivative of tangent x is secant squared x. So first times derivative of the second plus second tangent times derivative of the first. So that's secant x tangent x. And oh, it just keeps going on into the sunset. No matter how many times we compute the derivative, we're never going to get back secant x. So this is an example of a function that does not reproduce according to its kind. So we're going to illustrate how to solve a differential equation when the right-hand side is one of those troublemaking functions that doesn't reproduce according to its kind. If we were doing undetermined coefficients, the first thing that we'd want to do is find the complementary solution. Well, that's exactly what we do when we use variation of parameters. So we rewrite using operator notation. Here's our complementary equation, y double prime plus y equals 0. Complementary equation. And then we rewrite using operator notation. And then we factor out the y. And this exposes the auxiliary polynomial, phi of d. So we write the auxiliary equation, m squared plus 1 equals 0. And the left-hand side is just the polynomial phi evaluated at m. And we solve that, let's say, m squared equals -1, so m equals plus or minus square root of -1. So m equals plus or minus I. So our complementary solution, y sub c, is e to the power of m1 I beg your pardon. Our complementary solution is some constant times e to the m1x, so that's plus ix, plus some other constant, c2, e to the m2, which is negative ix. And we know what this turns out to be, don't we? This is the equivalent of some constant a times cosine of x plus some constant b times sine of x. There. That's our complementary solution. Okay, this is the whole idea behind variation of parameters. We get the complementary solution. And we remember that the complementary solution is part of the general solution of the original differential equation, because we get the general solution of the original differential equation by taking the complementary solution and adding to it a particular solution of the original differential equation. So we look at this and we say, you know what? We know that this is going to be part of the general solution anyway. Maybe somehow we can play around with this parameter A and this parameter B to turn this complementary solution into the general solution. And here's how we do it. Hey, Wayne, how are you? Good. Taking a lecture. We take the complementary solution which is a cosine of x plus b sine of x and transform these parameters into functions of x. So we take the parameter a, transform it into a function of x, a of x, not just a constant. We take the parameter b, transform it into a function of x, not just a constant. That's an incredible idea. I don't think people do LSD much anymore, but maybe whoever came up with this idea was definitely using mind-expanding drugs when they came up with this idea. A stroke of genius, to be sure. but an off-the-wall stroke of genius. Who on earth would think that this would actually work? Now, I guess I have to make a couple more comments about this. Not only does there exist a pair of functions, a of x and b of x, that make this work, it turned out that there are infinitely many pairs of these functions, a of x and b of x, that can transform the complementary solution into the general solution. And these functions, a of x and b of x, they do come in pairs. So they transform the complementary solution to the general solution. So this is going to leave us some latitude on solving for a of x and solving for b of x. we start off with two arbitrary functions, a of x and b of x. And we want them to be such that this is the general solution to our differential equation. Well, there are infinitely many pairs of a of x and b of x that will give us the general solution. So since we have two arbitrary functions, we're allowed to impose two restrictions on this pair of functions so that we'll actually get a unique pair, a of x and bx, that give us the general solution. Now here's the first restriction. There are infinitely many pairs of functions, a of x and b of x, and most of those pairs aren't going to give us the general solution when we plug in a of x and b of x. So the first restriction that we impose on this pair of functions, a of x and b of x, is that when we plug them into this function, we get the general solution. So that's our first restriction. So I guess the next thing that we should do is just compute y double prime and plug it in and just see what we have. So we'll do that. So we have y equals ax cosine of x plus bx sine of x. And before we can get y double prime, we have to get y prime. And son of a gun, we've got a product here. We've got a product there. We have to use the product rule. Okay, so we'll get first times derivative of the second plus second times derivative of the first. So that's the derivative of a of x cosine of x. Now we've got to do the same thing here. We'll get first, which is b of x, times derivative of the second, cosine of x, plus the second, sine of x, times the first prime, b prime of x. Oh, does that look like a mess or what? Now, let me just rewrite this a bit. Now, when we compute the derivative of this thing to get y double prime, we're going to use the product rule here, and here, and here, and here. Oh my goodness, we're going to get 8 terms. And we're going to have some a of x's. We're going to have some a prime of x's. We're going to have some a double prime of x's. We're going to have some b of x's, some b prime of x's, some b double prime of x's. That's an awful lot. So typically, it's in this point of solving the differential equation that we exercise our right to impose the second restriction. And typically, not always, but 95, 98% of the time, what we do is we impose the restriction that a of x and b of x are such that these two terms add up to 0. That is a prime of x cosine of x plus b prime of x sine of x equals 0. Now, the advantage of doing this is that we've just gotten rid of our a primes and our b primes, so that when we compute y double prime, all we're going to have are a of x's, a prime of x's, b of x's, b prime of x's. We're not going to have any a double primes or b double primes to worry about. So having asserted our right to impose our second restriction and choosing this as the restriction that we impose, this is what y prime turns out to be. Negative a of x sine of x plus b of x cosine of x. And don't forget, we're trying to compute y double prime. So compute the derivative of both sides here. And we get y double prime equals, we got a product here. So first, negative ax times derivative of the second cosine of x plus second sine of x times derivative of the first, so that's going to be negative a prime of x. Let's see, is that right? First times derivative of the second plus second times derivative of the first. We just differentiated this term. Now we got to do the same thing over here. First, b of x times derivative of the second, so that's negative sine of x, plus the second cosine of x times derivative of the first, b prime. And I'll put all my a's and b's up front. So negative ax cosine of x minus a prime of x sine of x. But you know what? Maybe I'll put my derivatives at the very rear. I have an ulterior motive for doing that. I'll move this term up here. So b of x sine of x, and this negative sign is that negative sign. Okay, now, negative a prime of x sine of x plus b prime of x cosine of x. And let me look over my handiwork and make sure I didn't do anything that I should be utterly ashamed of. I think I'm good. So now, plug y and y double prime into the equation. Y double prime plus y equals secant of x. This is what we're about to do. Okay, y double prime negative a of x cosine of x minus b of x sine of x minus a prime sine of x plus b prime cosine of x. okay, plus y, and y was a of x cosine of x plus b of x sine of x and remember what equation it is we're trying to solve? It's this one, y double prime plus y equals secant of x. So y double prime plus y equals secant of x. And that's equal to, well, let's see. These terms add up to 0. These terms add up to 0. And what we get is this thing, minus a prime of x sine of x plus b prime of x cosine of x. So when I've plugged all of this in to the original differential equation, that's what I got. Now, what the heck do I do with that? What on earth do I do with that? If I could get rid of a prime or b prime, I could solve the equation for the one of these functions that I didn't get rid of. If I can get rid of a prime of x here, I can solve this equation for b of x. Or if I get rid of b prime of x here, I can solve the equation for a of x. But how am I going to get rid of one of these functions? We'll use our second restriction. We assumed, let's see, what did we assume anyway? I'm thinking a prime x cosine. We assume that a prime of x cosine of x plus b prime of x sine of x equals 0. Well, that assumption is still valid. And we're free to use this assumption as many times as we want if it's to our advantage. So, somehow combine this equation with that equation to get rid of either a prime of x or b prime of x. So we have negative a prime of x sine of x plus b prime of x cosine of x equals secant of x. And then we got this thing, a prime of x cosine of x plus b prime of x sine of x equals 0. And I see negative a prime of x here and positive a prime of x here. And I'm thinking to myself, it sure would be nice if this were a sine of x instead of a cosine of x. Then I'd just add these two equations together and these terms would knock each other out. They'd cancel each other. Well, sometimes in the world of mathematics, wishes do come true. How do I turn cosine of x into sine of x? If I multiply cosine of x by tangent of x, let's see, cosine of x by tangent of x, that's cosine of x times sine of x over cosine of x. If I multiply cosine of x by tangent of x, these two things cancel, and I just get sine of x. That's how I'm going to do it. This is exactly how I'm going to do it. So, let me plot my strategy. I'm going to rewrite all of this again. A prime of x cosine of x plus b prime of x sine of x equals 0. And I'm going to multiply both sides of this equation by tangent of x. And oh, it's so nice, the right side here is 0 anyway, so I multiply 0 by tangent x, I'm still going to get 0. This is looking pretty good. It'll look even better once I multiply this side by tangent of x. There, is it showing now? Yes, it is, thank goodness. So tangent of x times cosine of x is sine of x. So we have negative a prime sine of x plus positive a prime sine of x That's going to be 0. Okay. And then I've got b prime here and b prime here. And I'm going to have b prime cosine of x plus b prime times sine of x times tangent of x, sine of x, tangent of x, equals secant of x, secant of x plus tangent times 0. Just secant of x. Okay. So let me simplify this a little bit. I have b prime of x times cosine of x plus sine of x times tangent of x. But tangent of x is sine over cosine. So this is sine squared over cosine of x. Oh, I sure wish this were a lot simpler. And I'm looking at this, and this looks kind of like something I'm familiar with. I know there's an identity that says cosine squared x plus sine squared x equals 1. Now, wouldn't it be nice if I could turn this whole thing into a 1? Well, I'll tell you what. I'll multiply this thing by cosine of x, and I'll multiply this side by cosine of x, and we'll let the good times roll. Cosine of x plus sine squared x over cosine of x. That whole thing times cosine of x. And now we got to multiply this side by cosine of x. Okay, let's see. B prime of x. Cosine times cosine is cosine squared. And cosine divided by cosine is 1, so we just have sine squared. And secant x times cosine x. Wait a minute. Isn't secant x... Oh boy, we need to start having quizzes again, don't we? Isn't secant x 1 over cosine of x? So this times that is just 1. Oh my goodness, this is really looking good. Oh, this is looking so good. Let's see, can I solve that? I think so. To get b of x, I just have to integrate with respect to x. Holy moly. Let me call this C1. Okay. Huh. I just solved for b of x. Holy moly. Now, find a sub x, or a of x. Our restriction, a prime of x cosine of x plus b prime of x sine of x equals 0. I think we can use that to find a prime of x, or a of x. See, b prime of x was 1. So this means a prime of x cosine of x plus sine of x equals 0. So a prime of x cosine of x equals negative sine of x and I guess a prime of x equals negative sine of x over cosine of x. I'm going to be able to do this one. Yeah. What is this really saying? A prime of x equals negative tangent x. Okay, that's what that's saying. So solve for a. Nah. Let me integrate both sides. That will give me a of x. So a of x negative, and the natural log of tangent, let's see, that's sine over cosine. let's see, according to our formulas, uh, integral of tangent x is natural log of secant, or a negative natural log of cosine I think I can do that. Okay, a of x, natural log of cosine of x plus c. And b of x, x plus c1. This is the general solution of our differential equation. And I'll point something out in just a second. This is our solution. I'm going to rewrite it okay. I'll distribute the cosine to both terms here. Natural log cosine of x times cosine of x plus c2 cosine of x and distribute the sign here. So I'll get x sine of x plus c1 sine of x Does that look familiar? Well, it does. This was our complementary solution. So this is our particular solution. And we do indeed have a general solution that's the sum of a particular solution plus a complementary solution. And if you remember, it's this complementary solution where we had a cosine of x plus b sine of x. It's this complementary solution that we reparameterized. We turned the a into a of x and the b into b of x. It's this complementary solution that we turned into the general solution by varying the parameters. And our reasoning was, well, we know that this complementary solution is going to be part of the general solution anyway. We got a cosine of x plus b sine of x. That's going to be part of the general solution. So maybe we can just take this complementary solution and turn it into the general solution by varying the parameters. This was a, we turned it into ax. This was b, we turned it into b of x. In another day or two, I will give a second lecture on variation of parameters because this is kind of a tricky topic. This is definitely a tricky topic. But in the meantime, I want to give you a couple of exercises to work on. Let's just try for right now, just 1 through 3. I'll give another lecture on variation of parameters with another example, and then I'll assign the rest of the A exercises. Page 203, exercises 1 through 3. We do these with variations of parameters. Take care of yourselves, exercise soundness of mind, and stay safe and stay healthy.